Hello and welcome again. Today we're going to talk about voltage and current, which are the main entities that we're going to deal with when we want to study and analyze circuits. We ended the last video learning how there is this mysterious entity called electric field, which is an omnipresent thing that is able to apply a force on any charge that falls in its domain. We also learned that the electric field is kind of annoying sometimes, and let's start by trying to understand better why. The electric field is what is known as a vector field. Field meaning that it is defined for every point of space. So you can ask, hey, what's the electric field here? And you can ask it for any point from here to beyond Jupiter, wherever you want. Vector meaning that the answer to what's the electric field here is not a number, but a collection of numbers, also known as vector. The answer would be, for example, the electric field here has three components, the x, the y and the z component, and their values are blah 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 blah. And this is for every single point of space. So it's really complicated to work with. This is a wire. Even if you don't know anything about electronics, you can imagine that a wire is not that complicated. It really doesn't do that much. But if you try to look at it with the electric field goggles, you have to compute the value of the x and the y on the z component of the electric field for every single point inside the wire, and since it depends on space, if I bend it, everything changes and just too much. We need to find another solution. Luckily, the electric field has another trick up its sleeve. It falls under the big category of conservative fields. A field gains the title of conservative if it has a few little properties, and if it does, it gains a lot of useful perks. One of these perks is the possibility to define a potential. This potential is an energy which is associated to the field itself. It is given to any particle which interacts with the field, like a charge in an electric field, just for being inside of the field. And it is like a sort of reservoir of energy, which is usually converted in kinetic energy, which is the energy of movement. This is just a fancy way to say that a particle which interacts with the field, it has the potential to move, because the field will move it. In order to better understand it, let's try with a more familiar concept, gravity. Gravity is a force which is very similar to Coulomb's force. The only difference is that gravity is only attractive, so bodies never repel because of gravity, and that it is millions and millions times weaker than the electric force. So it's a perfect example. What happens if I try to drop a ball? Well, for as long as I hold it, nothing. But if I let go, it falls. So we can think that the ball had the potential to fall for as long as I was holding it, and when it found the chance, when I let go, it actually fell. This is kind of philosophical, but in a more physical sense, when I held it, it had the potential energy, and this potential energy was converted into kinetic energy because it was moving when it fell. The potential energy depends from the height of the drop, because if I drop the ball from high up above, it's going to hit the ground with a big velocity, so it's going to have a lot of kinetic energy, and so in the beginning it had a lot of potential energy. On the other hand, if the height is very small, the kinetic energy right before the impact with the ground is going to be very small, and so the potential energy was very small. In the last case, If I let go of the ball when it's already touching the ground, it doesn't really fall. So we can say that it had zero potential. Voltage is the exact same thing. As we know, a charge in an electric field is going to receive a force equals to the charge times the electric field in that point. And so, for example, is going to get repelled. And so the charge, just like the ball, will have potential energy, because if I hold it inside the electric field, it doesn't move, but it has the potential too. So it has potential energy. The one difference with the example that I brought is that voltage is not exactly a potential energy, but it's potential energy per charge. That is because when the charge is big, Coulomb's force gets also very big, and so the charge is accelerated more and thus goes faster. And faster charge means bigger kinetic energy, and bigger kinetic energy means bigger potential. So this long chain means that if a big charge has more potential of a small charge in the same situation. And that is kind of annoying. So you can see that if the charge gets bigger, the potential energy also gets bigger. So we want to define our voltage as the potential energy per charge in a way that the voltage doesn't really depend on the charge itself. But voltage really does not depend on the value of the charge itself, so it's kind of constant. It is clearer to see if the charge goes to 1, so that the fraction potential over charge is equal to the potential. And you can see that voltage and potential correspond in this scenario. So why is it better? First of all, because it doesn't depend on the charge, so we don't have to worry about the charge. And second, because it gives a big picture of what's happening inside our circuit. We don't really want to deal with the energy of the single charge, because in our circuits there are going to be billions and billions of charges moving around. So dealing with every single one of them isn't really helpful, and so we have a high-level view, an overview of what's happening, as we have an average thing like potential energy per charge. But please notice that we aren't losing information, because yes, we have an average view, but we can retrieve everything up to the Coulomb's force, because from the voltage, if we need energy, we have energy per charge, we simply multiply by the charge if we're interested in its energy. And there is also a direct passage from voltage to electric field, and from electric field to Coulomb's force. So we have all the options that we want. Voltage is just very helpful and very useful, and so we like to work with it. But if we are wondering about more precise qualities, we can just get them very easily. Now, I have to confess that I lied to you. Remember when I said that the potential of the ball was 0 when it was touching the ground? Well, I actually lied. An object on the ground won't move because, well, the ground is on the way. It's just like when I was holding it, my hand was on the way, so the situation is no different. The trick here is that the potential, in the case of gravity, but also in the case of voltage, is not really a one-point thing. This is because, in the case of gravity, the potential depends on height. And the height of a point really doesn't make that much sense. Height is secretly a distance, and for a distance we need 2 points, A and B. The same thing also happens for voltage. The voltage of a single point doesn't make any sense. And it's not because we are limited in our knowledge or our instruments are wrong or whatever. It's mathematically nonsense. The voltage of a single point doesn't make any sense. What we are really interested in is the voltage across 2 points. One of which, again, is the point that we want to measure, and the other one is a reference point. What does it mean for our circuitry? When we're working with a generic component, represented by this rectangle in this case, we're not interested in the voltage of this point or the voltage of that point. We're interested in the voltage across the 2 points, usually indicated by this arrow. The butt of the arrow is placed onto the reference point and the tip is placed on the point of our interest. So the arrow is read as the voltage on the tip with respect to the bottom. By the way, did you notice it? We are no longer working with vectors. Don't get fooled by the fact that we represent voltage with an arrow. The voltage arrow is not a vector. It's just a way to distinguish between the reference and the point of interest. Voltage is really just a number, which by the way is measured in volts. This is a voltmeter. It is used to measure voltages. It is no chance that this tool has 2 probes. The black one is used to touch the reference point. The red one is used to touch the point of interest. So the number that we see on the display, right now it's 0 because it's not connected to anything, is the voltage between the black probe, the tip of the black probe, and the tip of the red probe. This is a 1.5 volts battery. Let's see what happens if I try to measure the voltage across it. I'll place the black probe, so the reference, on the bottom of the battery, and the red probe, so the point of interest, on the side labeled with a plus. What we measure is, well, about 1.5 volts. What did you expect from a 1.5 volt battery? What happens if I try to swap the 2 probes? Will something break? Will the universe stop existing? Ah no, I just get minus 1.5 volts. And that is a thing. It really only means that the voltage on the red probe was lower when compared to the black probe. So the charges on the red probe had less energy than the charges on the black probe. If you really think about it, you only have 2 ways of measuring voltage. This way or the opposite. And like with the battery, the flipped version of the same voltage is just the same thing but with a minus sign. But the 2 measurements are equally as good. Negative numbers are a bit annoying, so we will always try to guess the correct direction of the voltage in order to get a positive answer. I repeat, it's not correct because it doesn't make any difference, but it's just nicer to work with positive numbers. Unluckily though, it is not always possible. Beyond guessing, maybe help with a little experience, but doesn't change much, we can't do much more. So in our guesses we might get arrows which give negative answers, but I repeat, it's equally as valid. I'm gonna take 1 step in that direction. I'm gonna take minus 1 step in that direction. I was about to follow. The minus one step thing really made sense only because I said that direction, but there was nothing wrong to it. I didn't explode because I violated the rules of physics. I just decided a positive direction and then walked in the opposite way. So the same thing is really for the voltage. We choose the positive direction, what we expect, what we wish to be positive, but then we may be wrong and charges decide to make it negative. No big deal. Another instance where we cannot avoid negative voltages is when voltages start changing with time. We will really talk about the situations when we have a clearer understanding of how things work. But if voltages change with time, you might guess right at first that a voltage is like you expected, so the value is positive, but it may change with time and at some point it might get negative. But that's about it for voltage. Let's recap. First, in order to talk about voltage, you need to choose 2 points of which you want to know the voltage across, or sometimes called the voltage drop across the 2 points. Step 2, you choose a positive direction for the voltage, which corresponds to the action of choosing a reference and the point. Step 3, you deploy your solution methods and you get your answer. But careful, because it might as well be negative. Voltage is going to be our best friend from now on, but sometimes it doesn't give all the information that we need about the circuit. We always talked about how charges will start moving inside of an electric field, but never properly dealt with it. We need another entity, which is called current. Current is a measure of the flow of charges inside a conductor. If we take our wire from before, we can imagine of building an imaginary boundary inside of the wire and counting how many charges pass through the boundary. If we count the total amount of charge that passes through our boundary in 1 second, we divide the total number of charges by the time of our measurement. It could be 1 second, 2 seconds, or whatever. We get the current. So this is our wire with the charges moving inside of it. We draw our boundary, which lights up when a charge passes through it. We count the number of times it flashes, so the total charge, and we divide it by the time of measurement. The current is about 0.4 amps. If I speed up the particles, you're going to see how the boundary is crossed faster, so there are more charges that go through it every second. In this case, current goes to up to 1.5 volts. This is still incomplete, because just counting the crossings of our boundary doesn't tell everything, because see, there is a difference if charges are moving that way or this way, and we want to know it. So, just like for voltage, we will define a positive direction for current. It's the same thing, but we're going to count things going in one way and things going in the other way. The first ones count as plus, for example, and the second ones count as minus. The direction of the current is indicated by a small arrow which points the positive direction, but just like in the case of voltage, a positive current in one direction is the same thing as a negative current in the opposite direction. Notice how I am still talking about charges, even though in the previous video I said that the main carriers of charge are the electrons. So why am I not specifying electrons? The thing is that electrons are negative, and dealing with negative charges crossing, it's kind of like this. I am giving you 5 euros. I am taking from you minus 5 euros. See, the action was the same, but you can agree that the second description was a bit contorted. I'm taking minus 5, so it means that I'm giving 5. And the same thing really happens for electrons, because since electrons are negative, they bring this minus that we don't really like. So we prefer to consider current as the flow of positive charges. This used to confuse me a lot when I was younger, and I'm trying to explain it how I think would have helped me best to understand it, so bear with me. If this is our wire and there is a positive current flowing in that direction, it means that positive charges are flowing in that direction, and that is it. I initially believed that since the actual carriers are electrons, when I say that a current flows this way, in my equation I should put a minus sign because I should consider the current in the opposite. No, it's just not like this. It's much more simple. The real thing is that we really don't care about what electrons are doing. So even if they are not, you should really think that the two things are separate. You don't care about electrons. So positive currents are, okay, we guessed where the positive charges are going. Negative currents are, okay, there are positive charges moving. We were expecting them to go that way, but they're actually coming this way. So I tried to measure a current towards you, but the answer was negative, so I could stop here. If I want to make a step further, I could think, okay, so a positive current would have been in my way, but I should stop here. I do not have to care about electrons. And when I figured it out, it really annoyed me, because I was thinking as a high schooler, okay, I agree, this is simpler, but if we know that it is actually electrons moving as it is, then why are we not considering electrons a negative? No, the answer that my older self can give to my younger self is that we don't care, because we are not studying the physics of our circuits. We are seeing things from a higher perspective. If we want to get deeper into the detail of what's the electron doing, because it is maybe important for some reason, then we understand that if positive charges flow that way, so if I'm measuring a positive current in that direction, then electrons are flowing that way. But you should only worry about it in the physics context. Current, just like voltage, is a model of reality. It's not the exact representation of reality. So when I talk about an electron, the electron itself, I'm not talking about the electron as, if you know Plato, you might understand what I mean. But I'm talking about what represents the real thing in the real world that we decided to call electron. When we are talking about the electron, we are trying to mimic the real behavior of a particle as well as possible, and so we will deal with the problems in a certain way. But current is not used to see what particles are going to do. Current will be used to make circuits. And so when we build our model for current, when we build the idea of current, let's be nice with ourselves. Make it as simple as possible. Yes, it is electrons moving, but we don't care. We want to deal with positive charges, and so it is positive charges moving. That's it. It is gonna happen very rarely, but it is going to happen. We are going to have to worry about the electrons and actual positive charges moving in our circuits. But this will come in a long time when we will be talking about semiconductors. So, setting philosophy aside, we now know current. The steps to work with current are also very simple. First, we choose the point, yes, this time it's a single point, of a circuit of which we want to know the current. For example, this point of the wire. Second, we choose a direction for the current. Third, we deploy our solution methods and get the value of the current. Also in this case, the results might be negative, but that is not a problem. We finally got to know our two new best friends, which are going to stick with us forever. Voltage and current will be enough to know our circuits very well. There is still one third, a small friend that we will have to deal with, but he is used much less often and for specific purposes. So I'm going to introduce him when we actually need him. We know voltage and current, but we still don't know how to work with them. We know that we choose directions, we try to guess currents, voltages and points and whatever, but we don't know how to choose one with respect to the other. Is it really random? Can I really choose voltages everywhere, whatever I want, and currents everywhere, whatever I want? Or is there some helpful rule that might help us? How do we determine voltages and currents? We are going to learn these solution methods, at least the base solution methods, and we're going to develop in the next video. Thank you again for joining. Before the end of the video, I want to thank whoever gave me their feedback in my previous video, which I find really important. If you don't like the way I explained something because it was unclear, maybe I didn't stress something enough, maybe I stressed something too much, maybe I confused you, or maybe I said something wrong, please let me know. I will be more than happy to correct myself or try to explain things better. Of course, positive feedback is also appreciated, so if you like the way I explain something, I will try to make things that way, and just let me know. Thank you again for joining in this adventure, and see you in the next video.